Okay, I think we will now get started. Mm. So I have already shared my screen, but before I proceed, Aditya, could you please confirm you can hear me? Aditya Agarwal. Yeah, I actually could not hear you. You said something. Aryan, could you please confirm? Aryan Singh.
Yes, sir, you're audible.
Oh, okay, okay, great, great. Thanks so much. Thank you. Okay, very good. So I think we can now get started, and just to confirm that um, this is going to be chapter 8 of the book, and I am going to cover these topics today and during the 3 lecture hours in the next week, and up to that will be your syllabus for the test to be held during the week of 21st of February. And as we already mentioned that the test will be during this Tuesday's class, but the exact duration will let you know, so that once we have set the questions, you will know that in advance. Okay, I think with that, let us get started. And I believe you can see my screen. That is chapter 8, relational database design. So as we have mentioned in one of the initial lectures, that there are certain so-called good database designs and some not so good or bad database designs. Okay, so in this particular chapter we'll formalize what makes a design good or what makes it bad. And this is the example which was there previously also with us. And we have seen that, just to refresh our memory, that this table or relation has these 6 columns. And what we have here is that, as we see that the building name for a department and the budget for the department, those have been kept along with information about the various instructors in that belonging to that particular department. Now, of course, here we are assuming that the the building name, say, is unique for a department name, and also the budget is unique for a department name. Okay. So if we assume that, then we see that this physics Watson 70,000, or this building name Watson and budget of 70,000 for the physics department, that is repeated for every occurrence of um, an ID and a name for instructors. Okay, and same for some of the other department names, buildings, budgets. Also, if you remember, I said that it is, if we assume that this building and budget, these are specific to a department, then there is a lot of repetition. But even otherwise, that even say we assume that uh, the building name could be different for different for the same department, there could be multiple buildings, or the budget itself could be for a particular building of a particular department name. Even if that assumption is true, still keeping that information along with these instructors will not make sense, because if the same instructor belongs to the, say, department physics, and say two instructors, say Einstein and Gold, so if they belong to the physics department and sit in the Watson building, even though physics might be having other buildings, but there is no point repeating the budget for that department name and building combination. Okay, so of course, we understand that this budget building, these are more related to the department name than related to the instructor and their salaries. Okay. And as we had mentioned at that time, and in response to my question, one of you had correctly answered that the major problem is, of course, not about the additional disk space as such, because disk is quite cheap. But so that means storing that in a table by repeating this building name and budget for the same department name, that is not going to actually hurt us in a very big way. Rather, the difficulty is that if we change, say, the building name for Einstein, or the budget for this Einstein, we have to ensure that we also update it for gold, the second last row. Otherwise, what will happen is there will be inconsistency. Likewise, that if there is a new department which has just been set up, and what we have is that uh, we have started recruiting people. So instructors are there in that department, but it has not yet been assigned a particular budget information here. Okay. Or for example, if it is the other way, that there is indeed a department and a building and a budget, but we are yet to recruit people, then the information about building and budget for the department will not be representable here, because there is no instructor yet in the department. So we understand that notionally that there is something not quite good about these types of designs. But during the course of this particular chapter, we'll see what makes something good and what makes something not so good. So, as is mentioned, that of course that instructor department, we can split it up or decompose into two. One is for instructor, and the other is for department. And then what we can have is that we can have this particular instructor having only the instructor ID, name, salary, and department name, and the department name will have the department table will have department name, building, and budget. Okay. Now the question is that what makes these changes better can be understood formally when we talk about what is called functional dependency. Okay. So what it means is that if we consider that department name, building, and budget, these three columns, then for a particular department name, if I fix, so that means for the department name column, if we fix a value, if the value of building and budget, that means building itself and also the budget, they get fixed, then we say that this is something what is known as functional dependency. So functional dependency means what? Means we would say that building and budget are functionally dependent on department name, or we say that there is a functional dependency from department name to building and budget. And we use this arrow. So it is not about implication in that sense, but loosely sometimes people say that department name implies building and budget. But just remember that what it says is that this building and budget are uniquely determinable if we fix the value of the department name. Okay. So now if you see that what is good, what is bad kind of design, so this theory is built on the concept of this functional dependency. Okay. So what is important is that we try to decompose this type of a relation, which we know that it is not good, it has got redundancy and so on, or repetition of information. Then we would like to decompose it into so-called some smaller schemas. But when we decompose it into smaller schemas, we have to decompose it following certain rules. If we do not follow those rules, we will end up in situations which are really not good decompositions also. So that is what this second last bulleted point says, is that not all decompositions are good. Suppose there is this relation employee, where there is this ID, name, street, city, and salary. where we decompose employee into employee 1 with ID and name, and employee 2 with name, street, city, salary, you will see that we lose information, and such types of decomposition are what are known as lossy decomposition. So let us understand what we are trying to talk about here. Suppose we have this employee relation where the point to note here is that we have something nice, ID, name, street, city, salary. So as such, there is nothing wrong. But suppose we wanted to decompose it into two smaller relations, one with ID and name, and the other with name, street, city, salary. Okay. Now, if we had done this decomposition, then the idea is that when we decompose one relation into, say, two relations, then ideally by joining back those two relations using our standard SQL joins, we should be able to get back the original relation, meaning the data that was there in the original relation, we should get it back. Now, if we look at this example, through that process of join means through the process of natural join. If you look at this example, that if we break it up into these two relations, and then if we want to join, do a natural join, and of course this will be based on the name column, then as we can see that we are ending up into 4 rows in the joined the data that you will get by natural join of this decomposed relation. And it is quite obvious why it is happening, because as you can see that the value of name, that Kim, was the same for both the IDs. And then after we had done the decomposition and now trying to get back the original data by joining these two decomposed relations, we are joining on that common column called name due to the natural join, and the first Kim with 57766 will match with both the Kims in the second relation, and the second Kim with 98776 as ID also will join with both of the rows in the right hand side relation, and then we get back 4 rows, whereas originally there were only 2 rows. And this is what is called lossy decomposition. The reason why it is lossy is that, of course, you actually do not lose tuples, rather you gain more tuples if you do a natural join of the decomposed relation. But more tuples actually means that there is less information, because now what has happened is that the fact that this Kim North Hampton 67,000, that you cannot distinguish from the Kim Main Perry Ridge 75,000, both having this ID value of 57766, and likewise for the two Kims with 98776. And what it means is that you have lost the information which Kim is which one. Okay, so that's why it's called a lossy decomposition. So that means that whenever we are trying to decompose a schema into smaller schemas, the first and foremost requirement is that we do not end up in a lossy decomposition. We have to end up with some what are called lossless decomposition. Okay, so here is some example of lossless, often called lossless joint decomposition or lossless decomposition. Similarly, this lossy decomposition is also often called lossy joint decomposition. So suppose we have this decomposition of R, ABC. So you see ABC are the columns of the relation R, and we decompose it into AB and BC. Okay, and so that decomposition you can denote in terms of this relational algebra expression of projection of pi ABR, and the other is pi BCR. So you see that that is a compact way of representing what we mean by these two decompositions. And then this pi ABR natural join pi BCR, so that would result, of course, in this case, it is giving back the original set of tuples. So this is an example of lossless joint decomposition. So the point here to note is that we would like to always have decompositions. So we have some bad design, and if we decompose it nicely, we'll end up having a good design. And this how to do that, we'll use the notion of functional dependency. We'll formalize it very soon. And also we said that the first and foremost principle is that we should have a lossless decomposition. Now, with respect to this concept of decomposition and functional dependencies, there are a few uh, characteristics of relational schema and their decomposition, so that have been defined. And the first and foremost, and these are what are called various normal forms, and first of that is what is called the first normal form. Now the first normal form is not yet anything to do with functional dependency or decomposition or anything. It is fairly simple. It means that uh, in when we talk about any relation schema in our database design, so very first thing is that it should be in first normal form. And first normal form means that we should not have uh, something like say the data stored for example with comma like strings. So let me give you an example. So suppose if you remember, we had this notion of multi-valued attributes. So a student is an entity, and where I have roll number as a key attribute, and then we have mobile number, say a multi-valued attribute. And we said that decomposition would be such that we'll have for the student there will be one table, and for student mobile number there will be another table, where in the second table we'll have roll number and mobile number as the two columns, and two together will form the primary. I believe you remember that. Now, suppose instead of that we kept in the student table itself a column called mobile numbers, and there we kept all the mobile numbers of a student, uh, one separated from the other by commas. So one is 1 2 3 4 like this, the 10-digit number, comma, then another 10-digit number, and so on. Then it no longer remains in the first normal form. So very first normal form means that the data should be atomic. So these domains should be atomic. So there I cannot have these comma separated different numbers. Okay, so that is basically what is meant by uh, that this schema is in first normal form. If we try to keep data with respect to that comma, etc., then it will not be in first normal form. The other example says that if we had this notion of first name and last name as two attributes which made up the composite attribute name, then we should keep these two values, first name and last name, as two different columns in the table, and not try to combine them into one single column called name with both first name and last name, like Shomik Shural. You don't want to keep, because then you will have to process that itself to get the first part, second part all the time, and it is always better to have them separate, and you can easily concatenate them to get the full name. So the idea is that these are examples where it is not first normal form. But then also what is important is that if you see that if we have your roll number, so you have this roll number of say 19 CS something, most of you. Now in that case, what we see also that in that roll number, of course we have put in a lot of things, like 19 means the year in which you join, and CS is a department, and so on. So this in some sense is not atomic, but in another sense it is atomic, means the roll number itself is the full thing, whether you are trying to interpret that as these two digits as year of admission, and the next two digits as, or next two characters as your department. So if you try to do that, then it is absolutely not atomic. Okay, but if along with the roll number, if you keep say another column in that table called year of admission, and where you keep 2019, and the department you keep CS, then what happens is that your roll number will never be processed by breaking it up into these subparts. Rather, that is kept there ease of manual scrutiny of any information. So if it is printed, so by looking at that, it is easy for somebody handling things manually to figure out that what is the year of joining and the department. But of course, along with that, if we also print the year of joining as a separate column and also the department as a separate column, then actually you see that your roll number just as well could have been a non-intelligent number like 1 2 3 4 5 6 7 8, instead of having 19 CS 10034 or something. Okay, so so the point is that if you try to give meaning to the subparts of this roll number domain, then you are breaking the rule of first normal form. But loosely we will consider that that is in first normal form. And as long as it is not having things separated by commas, like I said, multiple mobile numbers or composite attributes we try to represent, then it is in first normal form. Okay, so this is the example of roll numbers, etc., as I mentioned. So our goal is to devise a theory for the following, as I said, that decide whether a particular relation R is in good form. In case it is not in good form, decompose it into a set of relations R1 to Rn such that each relation is in good form. The decomposition, of course, is a lossless joint decomposition. And this theory is based on two primary concepts. One is what is called functional dependency, and the other is what is called multi-valued dependency. So first we'll take up the concept of functional dependency. So what this concept is that it puts some constraints on the set of legal relations under this notion of functional dependency. We'll understand what it is. It requires that the value for a certain set of attributes determines uniquely the value of another set of attributes. And a functional dependency is a generalization of the notion of a key. So you have already studied this notion of super key, candidate key, primary key. So what it does is that it is a generalization of this notion of key, as we'll very quickly see. Okay. Now the definition of functional dependency. Let R be a relation schema and alpha is a subset of R. So when you say R is a relation schema, you understand that, and we'll be using this term again and again. When I write R be a relation schema, it means R is a collection of columns, column names. Okay. So if we say student, and then in parenthesis next to it we write roll number, comma name, comma department, then this is a relation schema. Okay, so this is what we denote as R, and this R will mean this collection of the columns. So R equal to the, in set notation, R equal to, in curly braces, roll number, comma name, comma department. So that is why this, when we say R is a relation schema, then we can treat it like a set. So that is what you need to keep in mind. And remember, a relation is basically that when you are having data in that included in that table. So this R is basically the set of column names. And when we say alpha is a subset of R and beta is a subset of R, we mean that a subset of those, that set of columns that make up R. So the set roll number, comma name is like alpha, or name, comma a department is like beta, and so on. Okay. So I hope this notation is clear, that alpha is a subset of R and beta is a subset of R. And the functional dependency alpha to beta, or that is beta is functionally dependent on alpha, or alpha functionally determines beta, holds on R if and only for any, now we are talking about the legal relations, lowercase r. So the relations are denoted with lowercase letter, and the schema is denoted by the uppercase letter. So functional dependency alpha to beta holds on R if and only for any legal relations whenever any legal relation R defined on the schema capital R, whenever any two tuples T1 and T2 of R agree on the attributes alpha, they also agree on the attributes beta. That is, T1 alpha equal to T2 alpha will imply T1 beta equal to T2 beta. Okay. So example RAB with the following instance of R. So if we have 1, 4, 1, 5, 3, 7, we see that A to B does not hold, because for 1, sometimes you have 4, sometimes you have 5. So 1 to 4, 1 to 5, so there are multiple values for the same value for A. So the functional dependency A to B does not hold. Here this A, when we write A, we denote it is a single column. And when we write in lowercase, we denote a set of columns. So this notation should be clear. So that's why alpha, and usually we'll denote with these Greek symbols alpha, beta to denote a set of columns, and we'll denote uppercase these English letters to denote these single columns. Okay, but we see that from B to A, if these 4, 5, 7 these are unique, then the corresponding values of A are also unique. So B to A, that functional dependency holds. But what is more important is that it should be such that next time suppose I add one more row which is say 6 7, then this b2a will not hold. So if we say that the functional dependency b2a does hold, then as is mentioned previously in that second bullet, that for any legal relation r on that schema r, so it should hold. That means that if we claim initially that the functional dependency b2a holds, then we will not be allowed to make an entry 6 to 7, sorry, 6 and 7, this combination 6 7 in this relation R defined on the schema AB. So what is important is that if we say that this holds, then it means that all tuples that today it is there or tomorrow I can add. So it is not that this is only for the current snapshot it holds. It means that this holds as a property of that schema, and hence for any time in future also I should not be allowed to make entries like 6 and 7 if this b2a does hold. Okay. So now so that is the basic concept, and now we'll complete this slide. We'll go through this slide and complete today's discussion. Is that now if we see that now you have already studied the concept of super key, now we can say K is a super key for relation schema R if and only if K functionally determines R. Okay. Now, when we say that this K is a super key, so here, of course, one point to note is that this K itself might be also a set of columns that is denoted as K here. Okay. So K need not always be a single, it only denotes this K. K is used to denote the concept of super key here. So this K itself could be a subset of the schema R. Okay. So if K functionally determines R means what? That means the values for these columns that are there in the set K, if we fix them, then the values for all the columns in the schema R will get determined. That means that if this K is fixed, then the rest of R, that means all the columns in R minus K gets fixed, and that in turn also means that the entire set of columns in R they get fixed. Okay, because K is functionally determining R. Okay, so now candidate key, now you see that we can now nicely define in terms of this functional dependency. So K is a candidate key of R if and only if, of course, K functionally determines R, that is the basic thing, and no proper subset of K will functionally determine R. So there is no alpha which is a proper subset of K for which alpha functionally determines R. And that is what actually you had studied in the context of candidate key, super key previously also, that a super key is a candidate key if it does not have any proper subset, which itself also is a candidate. Okay, or which also itself is a super key. So functional dependencies allow us to express constraints that cannot be expressed using super keys. So here we see that consider the schema like instructor, department ID, name, salary, department name, etc. So now we see that we expect these functional dependencies to hold. Okay, that department name will functionally determines building, and also ID functionally determines building, but we would not expect the following to hold, that is department name functionally determines salary. So this is what we can understand, that if we have this sort of a schema where we have put everything together, so we understand that this ID functionally determines building, and department name also functionally determines building. And as we see that we can say that ID and department name together, they form the super key. Okay, because but then that is not a candidate key because its proper subset, that is ID itself, also is a super key. Okay, so then ID of course is a candidate key, but department name itself is not also a candidate key because department name does not functionally determine ID, or department name does not functionally determine salary, because if I fixed a department name, say physics, the value of ID or the salary is not fixed because there could be so many people with the same department name. So what finally we are saying here is that in this particular schema, department name mind it, functional determines building, and department name functional determines budget. So department name functional determines both building and budget. So the notion of functional dependency, as we said, that it is a generalization of the notion of a key. So this functional dependency we can determine even on this particular schema from department name to building. We can also have it from ID to building, but of course that department name itself is not a super key. ID department name is a super key, but ID department name is not a candidate key because ID its subset is itself a super key. So ID is indeed a candidate key. Department name is neither a candidate key, of course, not a super key also. That means that, I mean, it's not a super key and hence it's not a candidate key rather. But we can define this notion of functional dependency. So finally, department with these six columns. And if we are given these functional dependencies, that ID to building and all sorts of other functional dependencies, including the department name to building and department name to budget. So from that, actually, we can conclude that this is not a good design. And why it is not a good design, and what is the definition of a good design in terms of functional dependency that we have studied, that is going to be there in the next slide, which we'll take up in our next class, that how we can use these functional dependencies to see which is a good design, which is not a good design. So I think I will stop here, and if there is any question, then I can answer, and otherwise we'll take it up from here in our next class. Is there any
Sir,
question?
I had a query.
Yeah, yeah, sure.
Like in this case, are we assuming that a department name, a particular department is situated in one building only? Because otherwise, it won't hold. Like if physics is in Watson building and Einstein building both, then that functional dependency should not hold, right?
Very good point. Yes, absolutely. So good thing is that here this who tells me whether this functional dependency holds or not. Okay, so it is again, as you remembered in the first few lectures, I said that um, we need to get these inputs from the users or the stakeholders, who can only tell us, and as you rightly pointed out, that whether a department can be housed in only a single building, that is some kind of a business logic. So the stakeholders can tell us that, see, for us, always the department name will be located in a single building. Hence, now when we database designers get to know that information, we'll put the functionality that department name to building holds. But if they say no, 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 the department name need not be in the same building, there could be multiple buildings in which the same department is located, then what you're saying is absolutely correct. Then we cannot put that in our notations, that department name functionally determines building. Okay, so that is very important, that as you said correctly, in that case definitely that functional dependency, or FD as we call it short, does not hold. But if the user tells us that no, indeed it will be always a unique building, then it will be department name to building that FD will hold. If we consider the other way, that if we ask, okay, so is it that a building can be there in two, sorry, a department can be there in two different buildings, so department to building does not hold. But is it true that the other way it holds, that if, say, uh, in a building only a single department can be located, although a department can be spread across multiple buildings, but wherever it is spread across, those buildings will be housing only one department, then it will be the other way. Building to department name, that functional dependency will hold. Similarly, as I mentioned, that if I consider the dependency between FD between department name, building, budget, is it that the budget is for a department, then department name to budget, that FD will hold. If the budget is for a department name building combination, then what FD will hold? Anyone can answer? What will be on the left hand side of the arrow and what will be on the right hand side? If the budget is not for a department but for a department name building combination,
Department name, comma, building on left and on right side budget.
Yeah, absolutely correct. So that now you can follow what I'm saying, right? So you see that this is very general, right? You can have some set alpha on the left and you can have some set beta on the right. Okay, and alpha to beta is the functional dependency. So that is what we wrote here. And again, as you said, as I mentioned and as you have understood and you answered correctly, is that whether this budget is for department name building combination or for a department name itself, we database designers will not know. So when we talk to the stakeholders, they will tell us that, oh, we maintain budget for every department for every building. Okay? So that is how we will know or get to know what the functional dependencies are. So it is very important to understand that these FDs is something that the users can tell us. And what we have in our mind notionally this is supposed to hold, that has no meaning. Okay, that we can come up with that, but then when we get it checked by the user, they will correct us if we are wrong. Very good question. Any other question?
Sir, I had one more query, but that's related to lab codes. So,
Hmm. Yeah,
yeah, so in
so
that,
that go ahead. We'll discuss it in the lab hours.
oh,
On Thursday we'll discuss. Okay, so anything else? Okay, so if there is no other question, so please, so Rahit was asking that. So please remind me at the very beginning on Thursday, we'll address the question because some people are not here, and if there is